everyone. This video is about deep learning, which is more advanced and complex compared to machine learning. However, deep learning is capable of achieving the most unexpected breakthroughs and marvels in the field of AI. Deep learning has made possible a world where machines not only follow commands but also learn, adapt, and make decisions like a human brain. By mimicking the intricate workings of the human mind, deep learning unleashes powerful algorithms capable of understanding patterns, recognizing images, translating languages, and much more. From autonomous vehicles to personalized recommendations, deep learning is the engine behind the cutting-edge advancements of today and the breakthroughs of tomorrow. So without much delay, let's have a look at what deep learning exactly is. Deep learning is recognized as a subset of machine learning, which itself is a component of artificial intelligence. As you can see in the adjoining figure, AI is a broad umbrella concerning everything related to making intelligent machines. Within AI, we have the subset of machine learning, and within machine learning, we have the subset of deep learning. Deep learning specifically utilizes artificial neural networks to model and address complex problems. This technology is inspired by the interconnected structure of the neurons in the human brain, enhancing the system's ability to learn from both labeled and unlabeled data. In other words, it is used for both supervised and unsupervised learning tasks, even for semi-supervised and self-supervised tasks. Now let's talk about the functionality of deep learning. Deep learning processes data using a structure of multiple interconnected layers made up of nodes or neurons. Each layer performs specific computations and transforms the input data progressively, refining the information as it passes through these layers. Due to its sophisticated architecture and feature extraction capabilities, deep learning is particularly effective in handling complex tasks. These include image and speech recognition, where models can classify images or understand spoken language with very high accuracy. For instance, deep learning has been successfully applied to various applications such as self-driving cars and virtual assistants, which rely on the ability to comprehend and interpret vast amounts of visual and auditory data. These tasks are very tough if you want to do with machine learning algorithms. It is deep learning that has enabled functionalities like chatbots and language translation too. Machine learning algorithms are not capable of achieving such high demanded tasks. The ability to handle both structured and unstructured data makes deep learning an essential tool in modern AI applications. It can efficiently process and learn from diverse datasets and give shape to most of the desired applications of today. Now the question is how deep learning is different from traditional machine learning. Traditional machine learning primarily utilizes simpler algorithms such as linear regression or decision trees, which often depend heavily on human intervention for tasks like feature selection. This means that experts must manually identify and select the most relevant features from the dataset, which can be time-consuming and require domain knowledge. In contrast, deep learning employs more complex architectures, specifically the artificial neural networks, as you can see in the diagram on the screen. The ANNs or any of the deep learning architectures eliminate the need for manual feature engineering. The architectures learn intricate representations directly from the data, often through multiple layers of neurons, that successively refine the data into higher level abstractions. For instance, in image recognition, the deep learning model might first learn to detect edges in the early layers, then progress to identifying the shapes, and ultimately recognize entire objects in the later layers. This automatic feature learning capability enhances the model's performance on complex tasks without requiring any predefined features. Now let's talk about the requirements. While deep learning offers great capabilities, it is very promising, but it has significant demands. The three major demands we'll be discussing today. Due to the complexity involved in deep learning, neural networks generally require large amounts of data for training to perform effectively. It thrives in an environment where vast datasets are available. It's not like you can work with 10,000 observations or 20,000 observations. You need lakhs and sometimes even millions and trillions of observations for deep learning algorithms to excel. This high data requirement is particularly relevant in domains like computer vision or natural language processing, where it is essential to capture the intricacies of the data, and you cannot do it with a small amount of data. Secondly, deep learning also tends to demand significantly more computational resources than the traditional machine learning algorithms. Training deep neural networks often requires high-performance computing infrastructure, including GPUs, to manage the intensive calculations required for optimizing the model's performance. The deeper the networks, the more computational power it requires. Therefore, while deep learning models have the potential for superior performance, they also necessitate access to advanced technology and considerable computational power. This is one reason why we have seen the rise of Google Colab, which offers the computational capabilities of Google servers to run machine learning and deep learning algorithms. Lastly, neural networks consume a lot of time in training. Several factors influence the time complexity of the deep learning algorithms. The number of layers in the network significantly impact the training time, as deeper networks generally require more computations during the backpropagation when the weights and biases are adjusted. Additionally, the number of trainable parameters and the specific operations involved, such as convolutions in the CNNs and the sequential models of LSTMs, also contribute to the overall time complexity of a model. This combination of high data needs, time complexity, and increased computational complexity means that deep learning typically seeks to achieve optimal performance in circumstances where traditional machine learning might struggle, particularly processing unstructured data like the images and the text. As a result, while deep learning can offer remarkable capabilities, as I said in the beginning, it demands and it is very crucial to have ample data, time, and robust computational resources to fully leverage its strengths. Now we have the key element of deep learning, the neural networks. Neural networks consist of three primary types of layers: input layers, hidden layers, and output layers, as you can see in the diagram on the left hand side. The input layer receives the initial data and consists of neurons corresponding to the features of that data. The hidden layers, which may vary in number, perform complex computations and transformations on the input data, allowing the network to learn the intricate patterns. Finally, the output layer produces the final prediction or output from the model. Now, if you're thinking what features are nothing but the data points or the salient observations which help differentiating one observation from the other. The functioning of the neural network is governed by two processes. One is forward propagation and the other one is the backward propagation. When data moves from the input layer to the output layer, this is known as forward propagation. The data moves through the network layer by layer, generating outputs based on the weighted connections, biases, and the activation functions. Conversely, backpropagation occurs during training, where errors from the output are computed and used to adjust the weights in the network by moving backward through the layers. That means during the back propagation, the data or the movement of data through the network is in a reverse direction from the output layer to the input layer. This adjustment process is critical for minimizing the error and improving the accuracy of the model's predictions. Each neuron within the network functions by processing input data through weighted connections. Neurons receive the inputs, apply the weights to these inputs, and then aggregate them, followed by the application of an activation function which takes the decision. This output is then transmitted to the neurons in the subsequent layers of the network, which continues the process of data transformation and refinement. Weights, biases, and activation functions. These are three very important parts of the functioning of a neural network. Weights play a crucial role in determining the strength of the connections between the neurons within the same layer within the different layers. It captures the relationships between the input features and the target outputs. They adjust during training, affecting the network's predictions. Additionally, biases are added to the neuron's output, introducing an additional degree of freedom that helps the model better capture the underlying data. Activation functions are also vital components. They introduce non-linearity, enabling the model to learn complex relationships within the data. Without these functions, the network would behave linearly, limiting its capability to solve real-world problems. Common activation functions include the ReLU, that is a rectified linear unit, sigmoid, softmax, ELU, and tanh. Each of these activation functions has a different way of working and hence a different way of contributing to the model's learning dynamics. Now let's talk about the applications of deep learning. There are various popular deep learning architectures like CNNs, convolutional neural networks, which are used for image analysis. We have RNNs, the recurrent neural networks, which are used for sequential data processing, especially text, and even for time series analysis. We have LSTMs, we have GRNs, we have GANs, that is the generative adversarial networks, and so on. We have different neural network architectures possible, which have led to breakthrough applications. So there are widespread applications across industries and verticals. Let's have a look at some popular examples. Voice assistants such as Apple Siri and Amazon's Alexa leverage the deep learning technology to understand and execute voice commands. These systems utilize deep neural networks to recognize spoken language, interpret the user intent, and generate appropriate responses, enhancing user interaction and engagement. As of date, they are capable of understanding the mood of the person too, and accordingly play the song, tell a joke, make coffee, or call the favorite person, and so on. Self-driving cars represent a significant application too. They utilize advanced deep learning algorithms to navigate and make decisions in real time. Through the analysis of vast amounts of sensor data, these vehicles can identify obstacles on the road, such as the pedestrians, the traffic lights, the animals moving around, and navigate complex environments safely. Deep learning helps autonomous vehicles learn from historical driving data, improving their decision-making capabilities. As you already know, Tesla is working regressively and with great attention on creating self-driving cars for our world. All of it is powered by deep learning. Medical image-based disease diagnosis have seen remarkable improvements. Thanks to deep learning, particularly the convolutional neural networks, as I was saying in the beginning, the CNNs are responsible for breakthroughs in image analysis. These models can efficiently categorize the images into the disease categories by learning to recognize the patterns and features, achieving accuracy levels that can surpass human performance in specific tasks. By leveraging computer-aided diagnostic systems in healthcare, a lot of patient outcomes can be improved. In agriculture, deep learning is supporting the smart farming practices. Techniques powered by deep learning are getting used for analyzing data from the IoT devices such as the weather conditions, the humidity, the temperature, and satellite imagery too, to ensure that the optimal crop management takes place. This application allows the farmers to predict the weather patterns, detect diseases, and therefore take appropriate measures to improve their crop yield. Lastly, we have cybersecurity. Deep learning is increasingly being used in cybersecurity as well. It assists in threat detection and prevention by identifying patterns and anomalies in data traffic. Deep learning algorithms are detecting potential cyber attacks. The proactive approach offered by these algorithms helps in dealing with security threats in an ever evolving digital landscape. It is enabling organizations to safeguard their networks more effectively. Sounds overwhelming, right? If you're keen on learning the deep learning technology and advancing your career, we have a well structured course waiting for you. Enrolling in our course allows you to gain expertise in sophisticated neural network architectures and model tuning techniques. This course covers a range of practical hands-on experience, enabling you to implement advanced techniques such as image classification, natural language processing, reinforcement learning, etc. By mastering these skills, you can significantly improve your proficiency and raise your demand in the job market. Don't miss out the opportunity to advance your career in deep learning. Thank you. Let's make deep learning your next breakthrough. I look forward to guiding you on this transformative journey towards becoming an advanced deep learning professional.